So believe it or not, this is now basically our last unit for sinusoidal functions, which is kind of crazy. I mentioned at the beginning that this unit was pretty short, and it is. There's not a whole lot to cover in sinusoidal functions. The most important part was just could we take the derivative given a few different situations. We do need to spend a tiny bit of time here on applications of sinusoidal functions, but not a lot. We need to review a couple of things, which is mostly this, and a lot of this came from both grade 11 and advanced functions anyway. We just need to remind you of a few things. Properties of periodic functions, so just some of the things you need to be aware of, or remind yourself that you already were aware of at least. These are some of the different properties of graphs given the function. So can we remember what the amplitude, the period, and so on is? Also, please remember, and we talked about this the other day, everything's in radians here. So we'll keep that in mind as well. For this first equation, it was y equals sine x, and the amplitude, remember amplitude was the distance from the middle, the sinusoidal axis, to the max or to the min. And the distance for that is just 1. So nice easy amplitude. I'm going to jump down to the sinusoidal axis. The sinusoidal axis is the horizontal line that is right in the middle of the maximum and the minimum, right? So for that y equals sine x graph, that was just the line y equals 0. But sometimes that changes depending on if I shift it up or down, and we'll see that in a minute. The period is how the length of time or the distance on the x-axis that it takes for this graph to repeat. And since we're in radians, it would be 2 pi. Remember that is equivalent to 360 degrees. Phase shift is if we're moving this graph left or right, but here we are not. This is the normal sine graph. It's starting at the point 0, 0. The reason we don't have to spend too much time on applications is the max and min part. When we've done derivatives, we've been able to figure out max and mins from derivatives, right? We go, I know how to find a max. A max happens where we have a horizontal tangent. So I'll take the derivative and set it to 0 and solve it. That should still work here, right? That principle should work throughout any type of calculus for any type of function, and it does. But sinusoidal functions are nice because we know information about them. As long as we know what the sinusoidal axis is and we know what the amplitude is, we can figure out what the max and the min is, right? For this one here, the sinusoidal axis is at y equals 0, and we go 1 above it. So the max is 1, the min is minus 1. We can tell that just by knowing information about this graph. Now, sometimes we'd want to know when that happens. And so maybe then it helps a little bit more to be able to picture the sine graph. And we're remembering that that's 2 pi to complete everything. Pi is right there. Pi by 2 is when we get our minimum, or excuse me, our maximum. And I don't think I can fit it in there. Our minimum happens at 3 pi by 2. So that's kind of nice though, right? We can figure that out without doing any calculations, no derivatives. We just think about what we know about the function. Frequency, I thought I better toss in. We don't use it too often, but the frequency is just 1 divided by the period. So your frequency in this case is just 1 over 2 pi, and that's not particularly exciting at all. Next one. Y equals 2 cos x minus pi by 3. So how does that change things? Well, now we've got a 2 in front. So that 2 is going to affect the amplitude. So now the amplitude is 2. Notice though there's no shift up or down. A shift up or down would happen at the very end, right? A +7 or a minus 85 at the end of the whole equation. So there was no shift, which means our sinusoidal axis is still y equals 0. The period also hasn't changed here. For the period to change, we would need a number either right there, which we usually label as k, or sometimes we'd put it in front of the brackets, which is even better. But there's no number there. My guess is we'll see it in the next one. There is a phase shift. The phase shift happens because of that pi by 3. So this whole graph is moving pi by 3 to the right. Remember, everything that happens in the brackets goes the opposite direction of what the sign suggests. So since it's a minus, we're going to the right. Let's do frequency, that's easier, 1 over 2 pi. The max and the min. The max, I think, is 2, right? Because our sinusoidal axis is at 0, and we're going 2 above. So our max is at 2, and our min would be at minus 2. And I think we can probably figure out when that would happen again. I'm just going to move that out of the way so we have more space. And we don't want this to be too much work, right? If you think about our normal coast graph, the normal coast graph looks like that. And so we normally have a max at 0, but this graph has been shifted pi by 3 to the right. So this max is at pi by 3 because everything moved over pi by 3 units. The min usually happens at pi, but it's been shifted over pi by 3 units. So that would be at pi plus pi by 3, which is 4 pi by 3. And granted, I'm doing that stuff in my head. If you want to write it down, you can. That's, I don't know, I find that's a heck of a lot easier than having to take the derivative and solving an equation. It's not, I don't think you get it automatically. You have to think your way through it a little bit, but I think it's easier. Okay, last one here. Y equals 5 cos 4x plus 2. Really important, notice the difference between the second and the third one there. Here, I've got brackets, and here I don't. Okay, so that plus 2 at the end isn't your phase shift. That's what's going to move the graph up and down. So that plus 2 makes the whole graph move up. That changes the sinusoidal axis to y equals 2. The amplitude is now 5. Whatever that first leading coefficient is, that's the amplitude. The period has changed this time. The period is usually 2 pi, but that 4, which usually we label as a k value, sorry, often we label as our k value, what that does, remember everything horizontally does things backwards. A 4 there is a horizontal compression. So it's taking this graph and compressing it by a factor of 4. So the period used to be 2 pi, but now we're dividing it by 4. So our period is now pi by 2. So this is a very small graph. Phase shift, we had none. Maximum we'll deal with in a second. The frequency, it's now 1 divided by pi by 2, which is 2 over pi. So that's our frequency. But I wanted to worry about that, the max and min stuff. The max, oh, sorry, let me back up. The sinusoidal axis was at 2. The amplitude's 5. So the maximum would be 5 units above the 2, which would be 7, right? 2 plus 5 gives us the 7. To get the minimum, we're going the other way. We're starting at 2, and we can go 5 below that. So our minimum occurs at minus 3. Now here's the nice part. Looks like I'm gonna have to erase this. Sorry, I'm gonna erase this and I'm gonna draw it back in again. Here is a not so good sketch, but it'll do the job of the graph we're talking about here. You that's really not so good, but again, it'll do the job. Let's assume that's the max right there. So our cycle's completed. We said in this one that the period's pi by 2, right? And forgive me, I really don't care about the height here. I'm worried about when the maximums and minimums occur. So I know the maximum occurs at, or excuse me, I know the graph completes by pi by 2 units. There was no phase shift, so I don't have to worry about it moving left or right at all. I'm wondering when that minimum occurs. Maximum's easy here, isn't it? The max is going to occur at 0. X equals 0. Because there was no phase shift. So with the cosine graph, it starts at x equals 0. But that minimum is right here. And to figure out where that occurred, it's just half of the period, right? The period was pi by 2. So the minimum occurs halfway to there, which should be pi by 4. So you can do some little interval divisions in order to figure out when those maxes and mins occur. And that's pretty much always the easiest way to do those questions. Okay. All right, we're just going to try one little example, and that'll wrap up our applications. There's a few to try at homework, which will help. But for the most part, it's just coming up with equations, which is what we're going to do here, and then recognizing maximums and minimums. I'm going to try and do something a little different. You may or may not have seen something like this in physics before. When you have a pendulum, you can represent the period of the pendulum with this little formula here. So the formula can be calculated as 2 pi times the square root of L, which is the length of the pendulum, so however long your string is, or however long whatever it is holding the pendulum, and G, which is our normal G, the acceleration to gravity of 9.8 meters per second squared. So the idea is, no matter how long that length is, we can make the calculation of what the period should be. Okay, kind of neat, because that pretty much, well, it means for the most part the weight of that pendulum is insignificant. Okay, you can calculate the period regardless of the weight at the end. So we're going to use that formula. That's not a formula that I would expect you to know. We're just using it in this example because I thought the example was kind of neat. So under no circumstances are you expected to know that formula. So here's our example. It says a pendulum has a length of 4 meters and an amplitude of 24 centimeters. So that's 24 centimeters right there. And our length is 4 meters. So for some reason, I've decided to make a ridiculously long pendulum. I have no idea why. Determine the period of the motion and an equation to represent it. So the period, we just had a formula for that, right? It was 2 pi square root of L over G, which is 2 pi square root. Our length was 4 meters. So put a 4 in, divided by 9.8. And there's units there, right? 4 would have been in meters. 9.8 is in meters per second squared, so actually our units line up fairly well. By taking the square root, it's going to be meters per second. They were both squared. The square root cancels out the meters, so our period turns out great. If you're into unit stuff, like you have to do a lot in physics. Sorry, anyway, I'm getting a little bit sidetracked. If you make that calculation, I end up getting 4.01. I considered using exact values there. I played around with it for a little bit. And it can be done, but it's not that nice, so I just changed it to a decimal right away. So there's our period. Period's equal to 4.01, approximately. Now we're trying to come up with an equation to represent this. An equation to represent the motion of the pendulum swinging. So what could I call that? Well, let's call it M. M of t. The motion based on time. And I know it's going to be a sinusoidal function because it's going to go back and forth. So I could either use sine or cos. I think I'm probably going to use sine. By picking sine, I'm assuming that this pendulum is starting at its rest position in the middle and swinging back and forth. A swing to the right would constitute a positive motion. So over here, that's going to be a positive distance from the center. Over here would be a negative distance from rest position. So I need a number here, sine of kt. Now I don't think we need a phase shift, so I don't need to worry about putting a number after that, and I don't need to worry about moving the sinusoidal axis up or down at all. I hope you remember doing questions kind of like this back in grade 11. Basically, you just have a motion like this, right? The pendulum's going back and forth. This spot right here represents that point. The location there would be this point. The total time to complete this was 4.01. And we know the amplitude was 24. That distance there is 24. But the sinusoidal axis is y equals 0, and there wasn't a phase shift. So if I can figure out A and K, we're good to go. A is easy. That A is always just our amplitude. So that's 24. Now, one thing that's come up in the past, which people have asked me about, is the units. We left the length in 4 meters and the amplitudes in centimeters. That is okay because we were just using that length of 4 meters to calculate our period. And we actually kind of needed to do that because the 9.8 was in meters per second squared. So keeping the units the same was a good idea there, keeping the 4 in meters. Now we need to know the K value. If I back up for a second, the way we calculated K up here, or excuse me, I guess we knew K. Actually click that so we can see it again. What we did was we were trying to figure out the period, right? Sorry, I'm going to erase this for a second so I have more space. The way we got the period was we went 2 pi divided by the K value. So now I'm trying to figure out what K is. If I rearrange that equation, K is equal to 2 pi over the period. And so that's what I need here. If I'm trying to figure out the K value, K is equal to 2 pi divided by the period, and we figured that out was 4.01. So if we punch that in the calculator, I get a K value of about 1.57. And again, I'm still rounding a bit, but I'm okay with that. So there's our function. The motion of this pendulum can be described as 24 sine 1.57 t. I guess one of the things, I'm not going to ask it for part B. You could ask what the max and the min was. It's really a boring question, though. You can tell just by looking at the thing. You didn't even need an equation for that, I don't think. If the amplitude's 24 centimeters, the highest it goes or the furthest it goes is 24 and minus 24. So I hope you're seeing a little bit of how max min isn't that interesting. This is what I wanted to show you, is just remind you how we can do velocity. This was a motion equation, right? So we could think of it as a displacement. I didn't label it d of t, I intentionally chose m of t. But if we want to calculate the velocity function should just be the derivative of the original, right? Velocity is the derivative of displacement. Acceleration is the derivative of velocity. So if I take the derivative of this one, it would be 24. Sine, derivative of sine is cos, so cos of 1.57 t. That's the derivative of the outside. And I have to multiply that by the derivative of the inside, which is just that 1.57. So nice, easy derivative, relatively. I'm trying to figure out the velocity after 3 seconds. So we'll just sub in a 3 here. How am I going to write this? 1.57 3. You probably have to be careful putting this in your calculator. Your best bet to use a calculator, again, make sure you're in radians, is, well, if you just do that part first, might be the easiest. Or just be really careful with brackets as you're entering it. But I got, hopefully, minus 0.09 as your velocity. And I don't know, when I first got it, I thought, oh, that's weird. I got a negative answer. We don't usually get negative answers. So I was a little bit worried about what the negative meant. I didn't care about the number so much. I just wanted to remind you of how we could calculate the velocity. But remember what a negative velocity means. A negative velocity means that we're going backwards. So with this pendulum, not sure how well I can show it here, but this pendulum is going back and forth, right? Keeps going back and forth like that over and over and over again. So what we would have is if it's swinging this, whoops, if it's swinging this way, you'd have a positive velocity going forward. That could even be here, right? All the way over, that would be a positive velocity. Or this way, it's coming back. So this isn't telling us too much that we get the negative 0.09, but what it is telling us at least is it's on the path back to the left. Okay, that's really about all there is for applications. Again, it'd be worthwhile for you to try some of the homework questions because there's a few different things that we can ask. For the most part, you just need to be aware of how to create some of these equations again, how to recognize from particular equations what the maxes and the mins are. And I think you'll find more often than not, it's much easier to just think about the equations rather than trying to set the derivatives. But if you're feeling a little gutsy, If you see some of the questions and it asks you to find a max or a min, try taking the derivative and setting it to 0 and see if you like that method any better. I don't think you will though.